Example 15.2 asks us to write the given function's equation as a product of linear factors. So when you see the language product of linear factors, that means we are wanting to create a linear factorization. So of course that means the linear factorization theorem would apply. So taking a look at the given equation here, we have f of x equals x cubed minus 3x squared plus x minus 3. And the first thing I want to check is the degree of this polynomial. So the degree of f, which will be based off of that leading term, is going to be 3, which is certainly greater than 1. So we can apply the linear factorization theorem. And the linear factorization theorem says then that we should be able to write f of x as a times x minus c1 times x minus c2 times x minus c3. So one of the implications of the linear factorization theorem is that the number of zeros slash the number of factors is always going to be equal to the degree of your polynomial. I would recommend going ahead and adding that to your notes on the linear factorization theorem. So degree 3, 3 factors, 3 zeros. Now let's go ahead and find the zeros for this function, and we can use those to write the linear factorization. So back over to the equation. This equation is set up really nicely for us to try the grouping technique. So f of x is going to equal x squared times x minus 3. And for that second group, the GCF is just going to be 1. So you'll want to, I know it seems kind of trivial to do that, but if you'll just pull out the 1, then it'll say 1 times x minus 3. So now we can have the x minus 3's in common, and we can pull that out as a common factor, leaving us with x squared plus 1. And as far as traditional factoring techniques go, we won't be able to factor this any further. So now I'm going to go ahead and do the 0 calculation by letting f of x be equal to 0, and then I will get the following two statements. 0 equals x minus 3, or 0 is equal to x squared plus 1. The first statement tells me that x is equal to positive 3. The second statement then says that negative 1 would need to be equal to x squared, and taking the square root of both sides is going to get plus or minus I to be equal to x. So there's two imaginary zeros, and then there's the one rational zero, for a grand total of 3 zeros. So going back over here to where we started setting up the linear factorization, I'm going to let c1 be equal to 3, c2 is going to be equal to I, and then c3 is going to be equal to negative I. And that will take care of everything I need to plug in to each one of my factors. But I also have to think about what I need to represent for A. A is supposed to represent the leading coefficient for your linear factorization. Well, the leading coefficient there is going to be the same as the leading coefficient you have when you're in standard form, which in this case is an implied 1. So I'll go ahead and also let A be equal to 1, and then I would get the following statement. F of x equals 1 times x minus 3 times x minus I times x minus negative I. And that lead coefficient of 1 can still be implied even if we're in factored form. So I can just drop that, making the first factor just x minus 3. Second factor will still be x minus I. And then the third factor, I'm going to write that as x plus I. And that gives us the linear factorization.